6 humans walked on the moon, 12 boots pressed into dust, 240,000 miles from Earth. Then, in December of 1972, we left, and we never went back. Over 50 years of silence. We will uncover the radiation walls surrounding Earth, the razor-sharp dust that destroys everything it touches, the political collapse that killed the greatest mission in human history, and the terrifying medical realities waiting for anyone who dares go back. If you enjoy what we do here, a like and subscribe keeps this channel alive. Brace yourselves. We begin. The last human footprint on the moon has been sitting untouched for over 50 years, and almost nobody asks why. Eugene Cernan climbed the ladder of the lunar module, looked down at his own boot print in the dust, and became the last human being to stand on another world. That was December 14th, 1972. And in all the decades since, not a single person has gone back. Pause on that for a moment. We live in an era where a handheld device can video call someone on the other side of the planet in real time. We have built space stations, launched telescopes that peer to the edge of the observable universe, and sent robotic probes past the outer planets. Yet the closest object in space to us, a rocky sphere 240,000 miles away, has sat completely untouched by human hands for over half a century. People assume the answer is simple. They say we already did it, so why repeat it? Or they say the technology just needs to catch up. Both answers feel reasonable. Both are wrong. The real story is layered, and every layer is more uncomfortable than the last. When Apollo ended, NASA had already approved 3 more moon missions. They were planned. The hardware existed. Apollo 18, 19, and 20 were on the books. Then, in the span of a few political decisions, all 3 were cancelled. The rockets were real. The astronauts were training. The missions died on paper, in budget meetings, far from any launch pad. That decision left something strange behind. Eugene Cernan's boot prints are still there, preserved perfectly. The moon has no wind, no rain, no erosion. Those prints could survive for 1 million years unchanged. A monument to the moment humanity touched another world and then turned around and went home. But here is where the story shifts, because the reason we stopped going was never just money or politics, though both played enormous roles. Beneath those surface explanations were harder truths, physical ones, medical ones, engineering ones that the original Apollo program either solved just enough to survive or quietly chose not to fully confront because the mission had to happen, and the timeline was brutal. The space between Earth and the moon is not empty, it is filled with radiation. Charged particles moving at enormous speed, funneled by magnetic fields, capable of damaging human DNA on a cellular level. The Apollo astronauts crossed that zone in about 3 days. They got lucky with solar activity. Some of them received doses at the high end of what engineers had calculated as survivable. One major solar storm during transit, and the story of the Apollo program ends very differently. Nobody cancelled future missions because of that danger alone. But that danger never went away. It waited. And the longer a mission stays, the more it accumulates. Even on the surface, the moon is hostile in ways that sound almost personal. The dust there is unlike any dust on Earth. It is ancient, unweathered, and microscopic. Its edges are jagged at a level too small to see. It clings to everything. It scratched visors, jammed equipment joints, and coated spacesuits within hours of surface activity. Astronauts tracked it into the cabin. They breathed it. The Apollo missions lasted a few days. A future lunar base would need humans to live there for weeks, months, possibly years. That dust becomes a different problem entirely. 50 years of boot prints, 50 years of silence. And the deeper you look, the clearer it becomes that we did not stop going to the moon because we finished. We stopped because what came next was harder than anyone wanted to say out loud. What those astronauts actually experienced up there, the things they saw and felt that never made the press conferences, reveal something about the moon that changes everything. What the Apollo astronauts actually saw when they looked back at Earth from the lunar surface, and how it changed them forever. Standing on the lunar surface, you look up, and there it is, Earth, hanging in a black sky that never changes, never brightens, never dims. A marble of blue and white, perfectly still, utterly alone. And the first thing every astronaut reported was the same feeling: fragility. Edgar Mitchell, Apollo 14, described it as a sudden and overwhelming certainty that the universe is conscious and connected. He came home and spent the rest of his life researching human consciousness. He never fully returned to the person he was before. Alan Bean, Apollo 12, stopped talking about engineering after he came back. He became a painter. Every canvas he made for the rest of his life was about the moon. He mixed actual lunar dust into his paint so that every piece contained something real from the surface. Buzz Aldrin landed on the moon at the height of his career and came home to a depression so severe it nearly destroyed him. He wrote about it openly years later. The mission was the peak of everything. Everything after felt smaller. The moon gave him the greatest moment of his life and made the rest of it harder to live. These are confirmed accounts, documented on record. 12 men went to the moon. Several of them had religious experiences. Several of them had psychological breakdowns within years of returning. None of them were fragile people. These were military pilots, engineers, and test pilots selected from thousands of candidates specifically for their emotional stability. What the moon did to them matters because it tells us something important about what extended lunar missions would do to future crews. The experience Edgar Mitchell described has a name now. Scientists call it the overview effect. It is a confirmed cognitive shift that occurs when humans see Earth from a distance significant enough to take the whole planet in at once. Researchers have studied it in astronauts from multiple countries and multiple eras of spaceflight. The effect is real and measurable. It rewires how the brain processes belonging, threat, and meaning. From the moon, the effect is more extreme than from low orbit. Earth does not dominate the sky the way it would from the International Space Station. It is smaller, distant, a single object among many. That visual shift produces a psychological shift that no amount of training fully prepares you for. Now consider a crew spending 6 months on a lunar base. They would experience this every single day. Researchers studying long-duration isolation have found that prolonged exposure to high-stakes environments, combined with restricted social contact and no escape, produces predictable psychological deterioration over time. That is in Earth-based simulations. Add the overview effect on top of it. Add the knowledge that rescue is days away at minimum, and that no one has ever done this before. The psychological architecture of a lunar base is one of the most under-discussed challenges in the entire return program. And there is something else. Something the astronauts noticed and described carefully, but that scientists still have no clean explanation for. On the lunar surface, in the absolute silence, several Apollo crew members reported hearing sounds, whistling, music-like tones, inside their helmets with no external audio possible. It was logged, investigated, attributed at the time to radio interference. Decades later, released recordings confirm it happened. The explanation remains incomplete. The moon changes people who go there. That fact is scientifically documented. What it does to people who stay there for months is something we have only begun to model. And before any human gets the chance to find out, they first have to survive getting there. The Van Allen radiation belts. The invisible wall of charged particles that wraps Earth and makes leaving it genuinely dangerous. Leaving Earth sounds straightforward enough. Rocket up, clear the atmosphere, and you are in space. But space does not begin with emptiness. It begins with a trap. Surrounding Earth are two enormous zones of radiation, called the Van Allen belts, named after the physicist James Van Allen who discovered them in 1958. They are shaped like two massive donuts stacked around the planet, invisible to every instrument except a radiation detector. The inner belt sits roughly 1,000 miles above Earth's surface. The outer belt extends out to about 25,000 miles. To reach the moon, you have to pass through both of them. The belts are filled with charged particles, mainly protons and electrons, captured from the constant stream of energy the star at the center of our solar system releases. Earth's magnetic field traps these particles in looping paths around the planet. The result is a radiation environment intense enough to damage electronics, degrade materials, and penetrate human tissue at the cellular level. Inside those belts, the radiation is not lethal in a single moment, the way a nuclear explosion would be. It works more like heavy, invisible hail hitting every cell in your body simultaneously. DNA strands absorb energy. Some repair, some do not. The more time you spend inside the belts, the more cumulative damage your biology accumulates. Too much, and the body cannot keep up with the repairs. Cancer risk rises sharply. Immune function drops. Apollo astronauts passed through the outer belt in roughly 30 minutes on the way out, and another 30 on the way back. Engineers plotted trajectories specifically to minimize belt exposure. They chose the fastest crossing path available. Even so, some astronauts received radiation doses that reached the upper boundary of what occupational safety standards considered acceptable for an entire year of ground-based work, delivered in a single crossing. A team of researchers studying the long-term health of Apollo astronauts published findings showing that those who flew to the moon died from cardiovascular disease at roughly 4 to 5 times the rate of astronauts who only flew in low Earth orbit and never crossed the belts. That study is confirmed, peer-reviewed, published in scientific reports in 2016. 4 to 5 times. The Apollo astronauts were not shielded particularly well against the belts, because the engineers of that era had to make brutal trade-offs. Every pound of shielding added to the spacecraft was a pound taken from fuel, life support, or landing gear. They chose survival by speed, crossing fast and accepting the dose. Modern spacecraft designs account for this more carefully, but there is no version of a moon mission where the belts disappear. Every crew that leaves Earth's orbit crosses through them, every time, and a crew making multiple return trips or rotating on and off a lunar base accumulates that dose repeatedly across a career. There is currently no shielding material light enough to carry into space that fully blocks the types of radiation inside the belts. Researchers are testing new approaches, including polyethylene-based panels and water wall designs that use the spacecraft's own supplies as a buffer. Progress is real. A complete solution is still years away, and the belts are only the first hazard. They end at about 25,000 miles away. The remaining 215,000 miles offer a different threat entirely, one that the belts actually partially shield you from while you are inside them. Once you clear the belts, that protection vanishes. How Apollo engineers calculated an acceptable radiation dose for astronauts, and what acceptable actually meant in human terms. Someone had to decide how much radiation a human being could absorb on the way to the moon and still be considered safe. That decision fell to engineers, physicists, and medical officers in the 1960s, working with incomplete data, enormous political pressure, and a timeline that gave them almost no room to slow down. What they produced was a number, a limit, a dose threshold that defined the boundary between a mission that could proceed and one that could not. Here is what makes that number chilling. The radiation limits they set for Apollo astronauts were not drawn from a deep well of established science. Radiation medicine in the 1960s was still young. Most of what scientists knew about radiation's effects on humans came from two sources: the survivors of Hiroshima and Nagasaki, whose exposures were studied in enormous detail, and nuclear industry workers, whose occupational doses were tracked over years. Neither group mapped perfectly onto an astronaut crossing the Van Allen belts at high speed in a thin aluminum capsule. The physics was different, the particle types were different, the exposure duration was different. Engineers had to extrapolate. They built models, ran calculations, and arrived at a threshold that they believed represented an acceptable increase in lifetime cancer risk. Acceptable. That word carried enormous weight in those rooms. The accepted risk was set at roughly a 1% increase in the probability of a fatal cancer over a lifetime. That sounds small. In the context of sending a human being into an environment no human had ever entered before, with instruments that could not fully characterize what was out there, it represented an enormous act of institutional faith in math that had never been tested at scale. The astronauts knew. They signed off. These were men who had already accepted daily risk as military test pilots, flying experimental aircraft that killed their colleagues with regularity. A calculated cancer risk was, to many of them, a manageable abstraction compared to the immediate dangers of the mission itself. But the calculation had a flaw. It assumed stable solar conditions. The one variable the engineers could not control, and could only partially predict, was what the star at the center of our solar system was doing at any given moment. In August of 1972, between the Apollo 16 and Apollo 17 missions, a solar particle event occurred that researchers later described as one of the most intense of the entire 20th century. The energetic particle burst it released would have delivered a radiation dose to any crew in deep space that exceeded the Apollo safety limits by a potentially lethal margin. Apollo 16 had landed and returned. Apollo 17 had not yet launched. The window between them was roughly 4 months. That event detonated in the exact gap between missions. Pure chance. If Apollo 17 had launched on its original schedule and been delayed, or if Apollo 16 had been delayed even slightly, a crew would have been in transit during that event. The trajectory they were on gave no meaningful protection. The capsule shielding was designed for the expected environment. An event of that magnitude was within the range of what could happen, and engineers knew it. They accepted the probabilistic risk and pressed forward because the mission had to fly. The astronauts who flew Apollo survived. They were fortunate in their timing as much as anything else. The radiation risk did not end with their landings. It accumulated in their bodies across the years that followed. And that risk, the deep space radiation that waits beyond Earth's protective magnetic field, is still there, still unresolved. And it has grown more complicated the more carefully scientists have looked at it. The moon's surface is covered in a razor-sharp dust called regolith that destroys equipment, lungs, and spacesuits in ways engineers still struggle to solve. Every Apollo astronaut came back dirty. That sounds trivial. Astronauts working on another world get covered in dust. Of course they do. But the dust on the moon is unlike anything on Earth, and understanding what it actually is explains why it became one of the most serious unsolved engineering problems facing any future lunar mission. On Earth, dust is worn smooth. Wind, water, and friction grind particles over thousands and millions of years until their edges round off. Pick up a handful of beach sand and hold it up to the light. Those grains have been tumbling against each other for so long they look almost polished. Lunar dust has never had that experience. The moon has no wind, no water, no erosion in any familiar sense. Its surface particles, called regolith, form through a completely different process. Micrometeorites rain onto the lunar surface continuously over billions of years, pulverizing rock into fine powder. That powder is then exposed to ultraviolet radiation from our star, which electrostatically charges each grain. The result is particles shaped like broken glass at a microscopic scale. Jagged, charged, sticky. They cling to everything they touch, because the electrostatic charge makes them attract to surfaces. They do not brush off cleanly, they embed. Harrison Schmitt, the only professional geologist to walk on the moon, reported having his vision impaired by dust on his visor within hours of surface activity. Astronauts tracked it into the lunar module on their suits no matter how carefully they tried to brush themselves off. Inside the cabin, floating freely in microgravity, the dust became airborne. Several crew members reported symptoms similar to severe hay fever, scratchy throats, irritated eyes, congestion that persisted after the mission. Lunar regolith contains a mineral called ilmenite and various silicate compounds. Inhaled into human lungs, jagged silicate particles cause a condition similar to silicosis, a progressive and irreversible lung disease that miners on Earth develop after years of exposure to silica dust. Scientists confirmed in laboratory studies that lunar regolith particles are biologically reactive, meaning they cause damage to lung cells in a way that Earth-weathered dust does not. Apollo crews were on the surface for a maximum of about 3 days. The exposure was limited. A future crew living in a lunar habitat for 6 months or a year faces a categorically different risk profile. The suits themselves suffered. The abrasive quality of the regolith began degrading the outer layer of Apollo spacesuits within a single moonwalk. Joints became stiff. Seals showed wear. Engineers examining the returned suits found damage that, had the missions lasted significantly longer, would have compromised integrity. A suit breach on the lunar surface is a death sentence within seconds. NASA and private engineers have been working on dust mitigation for decades. electrostatic shields that repel charged particles, surface coatings that resist adhesion, airlock designs that prevent dust from entering habitats. Some solutions show promise in laboratory conditions. None have been tested at full scale on the actual lunar surface for anything approaching the duration of a real crewed mission. The moon coats everything it touches. The astronauts joked about it, but the engineers who examined the returned hardware understood what sustained exposure would mean. And the dust is only a surface problem. Beneath it, the moon holds a thermal environment that makes the surface look almost welcoming by comparison. Why the moon's 2-week-long day cooks one side at 250 degrees, while the other side plunges to negative 250 degrees. And what that does to machines. The moon rotates slowly, extraordinarily slowly. One full rotation takes about 29.5 Earth days, which means one side of the moon faces direct sunlight for roughly 2 weeks straight, while the other side sits in total darkness for the same period. There is no morning and evening to moderate the temperature, no atmosphere to hold heat or spread it around. The transition from light to dark is brutal and nearly instantaneous. On the sunlit side, surface temperatures climb to around 250 degrees Fahrenheit, hot enough to fry an egg many times over, hot enough to warp metals and expand materials beyond their designed tolerances. On the dark side, temperatures plunge to around negative 250 degrees Fahrenheit, cold enough to make metals brittle, cold enough to freeze lubricants solid, seize mechanical joints, and crack materials that would perform perfectly at room temperature. A lunar base experiences both. The structure, its power systems, its external equipment, all have to survive that full thermal swing cycling between those extremes across every 29-day period. On Earth, engineers designed for thermal ranges measured in maybe a couple hundred degrees total. The lunar swing exceeds 500 degrees from peak heat to peak cold. No terrestrial engineering environment matches that range at scale. Apollo hardware was designed for short stays. The lunar module sat on the surface for a maximum of about 3 days, always in a sunlit landing window, chosen deliberately to avoid the worst extremes. The astronauts were in and out before the thermal environment became catastrophic for their equipment. A permanent habitat changes everything. Solar panels must survive weeks of darkness, with no power input, requiring either enormous battery banks or nuclear energy sources to sustain life support through the long lunar night. Thermal regulation systems must cycle across a temperature range that would destroy most standard engineering materials without specialized coatings and structural designs. The thermal cycling also does something to the ground itself. Rock and soil that expand in heat and contract in cold, doing so over billions of years, create a surface layer that is mechanically unstable in ways that complicate construction. Foundations that work on Earth shift under these conditions. A habitat that seems secure during the lunar day could experience structural stress as the ground beneath it contracts during the lunar night. Engineers developing the Artemis lunar base concepts have proposed several solutions. Habitats placed at the lunar south pole take advantage of elevated terrain that receives near constant, though angled, sunlight. Small crater rims near the poles stay in near perpetual light, offering a relatively stable thermal environment. That is one of several reasons the South Pole has become the primary target for future human landing missions. The trade-off is that those same crater rims sit adjacent to permanently shadowed craters that never receive sunlight at all. And it is inside those shadowed craters that something was confirmed in recent years that completely changed the strategic value of the moon. Water, ice, confirmed, sitting in the coldest and darkest places on the nearest world to Earth. That discovery turned the moon from a destination back into a prize worth competing over. The mystery of the moon's magnetic field pockets, small, invisible shields scattered across the surface with no clear origin. The moon has no global magnetic field, no protective envelope surrounding the entire body the way Earth's magnetic field does. From a physics standpoint, that makes sense. The moon's core is small, mostly solid, and generates almost no magnetic activity. Without a churning liquid metal interior producing a dynamo effect, there is no field to speak of at the planetary scale. Except there are small patches. Scattered across the lunar surface are regions of localized magnetic anomalies, pockets where the rock itself carries a magnetic signature strong enough to deflect some incoming solar wind particles. These patches are confirmed. Orbiting spacecraft have mapped them. Scientists call them crustal magnetic anomalies, and they cover areas ranging from a few miles across to hundreds of miles wide. And the mystery is deep, because the moon should not have them. For rock to become permanently magnetized, it has to cool while inside a magnetic field strong enough to align its iron-bearing minerals. That means at some point in the moon's past, either the moon had a global magnetic field of its own, or something else produced a localized field powerful enough to magnetize specific regions of the crust. The first theory, confirmed by analysis of lunar rock samples, is that the moon did once have a global magnetic field, billions of years ago when its core was still partially molten and active. That field eventually died as the interior cooled. The magnetized rocks are fossils of that ancient era, locked in place. The second theory is stranger. Some of the strongest magnetic anomalies appear to be located on the exact opposite side of the moon from the largest confirmed impact basins. Scientists have proposed that when a massive meteorite struck the moon billions of years ago, the impact sent a shockwave through the entire body. When that shockwave converged on the opposite side, the collision of forces briefly generated enough energy to magnetize the crust at the antipodal point. Both theories have supporting evidence. Neither is fully settled. The exact origin of the strongest anomalies remains an open scientific question. What makes this more than a geological curiosity is what these patches might mean for a future human presence. Research teams have examined whether the magnetic anomalies could offer any meaningful protection from solar radiation to structures built inside or near them. Early models suggest the protection would be far too weak to replace engineered shielding for a crude habitat. A pocket magnetic field deflects some solar wind ions, but higher energy particles pass straight through. However, one of the most striking anomalies, a region called Reiner Gamma, visible from Earth as a bright swirling pattern on the western edge of the near side, has produced results in simulations suggesting the local field might create a small but measurable reduction in surface radiation exposure. Scientists want to study it more closely. The moon hides its history in its rocks, and that history keeps producing surprises the further we look. But any mission that wants to investigate these anomalies or survive the radiation environment around them has to first wrestle with a problem that ultimately killed the original lunar program from the inside: the bill. What the Apollo missions actually cost in today's money, and why that number ended the program before the science was finished. The Apollo program cost approximately $25 billion in 1960s money. Adjust for inflation, apply modern economic equivalents, and economists estimate the total program cost at somewhere between $150 billion and $300 billion in today's terms, depending on the methodology used. That is the cost of a small war, the cost of multiple generations of national infrastructure, the cost of a program that consumed, at its peak, roughly 4% of the entire United States federal budget in a single year. For context, the entire annual NASA budget today sits at around $20 to $25 billion. The Apollo program, at its height, consumed more than that every single year. The money flowed because of the Soviet Union. The space race was not an exploration program. It was a weapons program wearing an exploration costume. Every Saturn V rocket that lifted off was a statement about American industrial and technological power directed at a geopolitical rival. Congress funded Apollo because losing the moon to the Soviets was politically unthinkable, and winning it was a visible, unmistakable victory in a war fought mostly in shadow. Once Neil Armstrong stepped onto the surface in July of 1969, the political mission was complete. The United States had won. The argument for continuing to pour that level of funding into further missions became dramatically harder to make in congressional budget hearings. The Vietnam War was consuming money and public attention. Social programs were demanding investment. The Apollo program, suddenly victorious and lacking a new enemy to defeat, became a target. Apollo missions 18, 19, and 20 were cancelled not because the science was done. Geologists and planetary scientists were furious. They had barely scratched the surface, literally. 12 men had walked on 6 sites across a body roughly the size of the continental United States and Africa combined. The science was just beginning. The missions died because the political will that funded them had achieved its objective and moved on. What replaced them was the Space Shuttle program, an attempt to make spaceflight cheaper through reusability. That program launched in 1981 with a design that was an engineering compromise, shaped as much by Air Force requirements and budget constraints as by any coherent vision of where humanity should go next. The shuttle never left low Earth orbit. Humanity went from the moon to a vehicle that circled the planet at 200 miles up for 30 years. The cost problem did not go away, it transformed. And the decisions made in those budget rooms in the early 1970s set the trajectory for everything that followed, including two disasters that permanently changed how NASA understood risk. The political weapon NASA became during the space race, and how winning it also killed the will to continue. President John Kennedy did not set the moon as a goal because scientists asked for it. He set it because it was achievable within a decade, because the Soviets could not be certain they could match it, and because space had become the most visible arena in the competition between two superpowers who were otherwise circling each other with enough nuclear weapons to end civilization several times over. In May of 1961, Kennedy stood before Congress and committed the United States to landing a man on the moon before the end of the decade. The speech was made roughly 3 weeks after the Soviet Union sent Yuri Gagarin into orbit as the first human in space, a moment that landed in the American public consciousness like a gut punch. The Soviets had beaten America into orbit. They had the first satellite. They had the first human in space. Kennedy needed a goal the United States could credibly claim and win, and he chose it with deliberate calculation. Declassified documents and recorded conversations confirmed that Kennedy was willing to propose a joint moon mission with the Soviets if it would reduce costs and defuse the competition. He raised the idea with Soviet Premier Nikita Khrushchev in person. The Soviets declined. The race continued. What this context reveals is that Apollo's engine was rivalry, and rivalry has a finish line. Once Armstrong and Aldrin landed in July of 1969, America had what it needed. The remaining missions, 5 successful landings after Apollo 11, continued largely on the momentum of existing hardware and trained crews. But each one faced a harder political environment than the last. Public attention had shifted. The dramatic first landing could not be replicated. Subsequent missions were reported as almost routine by a press corps that had already written the historic story. Internally, NASA knew the program was contracting. The agency had been built around a specific mission with a specific deadline. When both were satisfied, the institutional structure that produced Apollo had no clear successor. Scientists pushed for a lunar base. Engineers proposed missions to Mars. Politicians looked at the price tags and the absence of a Soviet threat to match, and the proposals stalled. The space program that emerged from Apollo's shadow was smaller, more cautious, and permanently shaped by budget cycles rather than geopolitical urgency. That shift had one more devastating consequence. The engineering knowledge that built Apollo, began to disperse. The teams broke up. The contractors moved to other projects. The organizational memory that knew how to send humans to the moon started to dissolve. By the time anyone seriously tried to reconstruct what NASA had learned, they discovered something alarming. The blueprints existed. The knowledge of how to build the most powerful rocket in human history, the Saturn V, had partly vanished with the people who built it. The Saturn V rocket, the most powerful machine humanity ever built, and why we lost the knowledge to build another one. The Saturn V stood 363 feet tall. Fully loaded with propellant, it weighed 6 million pounds. When it ignited, its 5 first-stage engines produced 7.5 million pounds of thrust, enough force to launch roughly 50 school buses into orbit simultaneously. It remains, confirmed, the most powerful rocket ever flown successfully by humanity. It flew 13 times. Every single launch succeeded. Every crew it carried came home alive, and then it was retired. And the knowledge of how to build it began to erode in a way that engineers decades later would describe as quietly catastrophic. The blueprints survived. Paper copies, technical drawings, manufacturing specifications, they existed in archives. What did not fully survive was the tacit knowledge, the understanding carried inside the minds of the engineers and machinists who actually built the thing. When NASA engineers in the 1990s began examining the possibility of reviving or reconstructing Saturn V class capability, they ran into a specific and humbling problem. Certain components of the engine, particularly the Rocketdyne F1 engine that powered the first stage, had been manufactured using techniques that were never formally documented in sufficient detail, because the people doing them simply knew how to do them. They had developed methods through trial and error on the factory floor, refined them over years, and carried them in their hands and their judgment, rather than in any manual. Some of those people had retired. Some had died. The institutional memory was fractured. Engineers described trying to reverse engineer components of their own program, studying artifacts of an achievement they had made to understand how they had made it. Certain manufacturing techniques had to be reinvented from scratch. Metallurgical processes that achieved specific tolerances in the original engines required years of modern research to approximate, using tools and methods that did not exist when the original was built. The Space Launch System, NASA's current heavy-lift rocket designed to carry Artemis missions to the Moon, produces slightly more thrust than the Saturn V's first stage. It uses Space Shuttle main engines, already existing hardware, rather than a newly designed engine system. Part of that decision was practical. Developing an entirely new engine at the scale of the F1 from zero would have taken an additional decade and tens of billions of dollars. The lesson is painful. An engineering achievement, even a fully documented one, can be partially lost simply by allowing the human network that built it to disperse. Knowledge lives in people as much as it lives in documents. And people retire, people die, industries shift. The space race produced the most capable rocket ever built, and then allowed the conditions that produced it to dissolve within a generation. Rebuilding that capability has taken 50 years and still is not complete, and the cost and complexity of doing so was only one of the pressures shaping NASA in the decades after Apollo. The other pressure was fear, a specific, institutionally traumatic fear born from two disasters that changed every calculation the agency made. How the Challenger and Columbia disasters reshaped NASA's tolerance for risk and pushed human spaceflight into a decade of institutional fear. On January 28, 1986, the Space Shuttle Challenger broke apart 73 seconds after launch. 7 crew members died. Millions of people watched it happen live on television because a school teacher named Krista McAuliffe was on board, and classrooms across the country were tuned in. The technical cause was an O-ring seal failure in cold weather. The institutional cause, as the Rogers Commission investigation found, was that engineers at the contractor firm Thiokol had raised concerns about the O-ring's performance in low temperatures the night before the launch. NASA management overrode those concerns. The launch proceeded. Challenger was a management failure wearing the face of an engineering accident. 17 years later, on February 1, 2003, the Space Shuttle Columbia disintegrated during re-entry. 7 crew members died. The technical cause was foam insulation that had struck the orbiter's heat shield wing during launch, creating a breach that caused catastrophic heating during re-entry. Engineers had noticed the foam strike and raised concerns during the mission. NASA management determined the crew could do nothing about it and chose not to pursue the analysis further. Columbia was the same failure wearing a different face. 2 disasters, separated by 17 years, caused by the same institutional pathology. The pressure to launch, the pressure to proceed, the tendency to normalize risk that had not yet caused a catastrophe. After Columbia, NASA grounded the shuttle fleet for over 2 years. The agency underwent the most intensive safety review in its history. When flights resumed, the process for assessing risk had been rebuilt from the ground up with a new principle. Any engineer could raise a safety concern and force a formal review with documentation that management could not simply wave away. That was a genuine and important cultural improvement. It also made human spaceflight dramatically more cautious, more expensive per flight, and slower to execute. The gap in American human spaceflight capability that opened after the shuttle program ended in 2011 was not filled until SpaceX's Crew Dragon began carrying NASA astronauts in 2020. Nearly a decade of reliance on Russian Soyuz capsules to reach the International Space Station. For an agency trying to plan a return to the Moon, both disasters left a specific psychological mark. NASA became an organization acutely aware of what happens when institutional confidence outruns actual evidence of safety. The caution that produced was real and defensible. It also made bold timelines almost impossible to meet, and the timelines for returning to the moon have slipped repeatedly. The Artemis program has rewritten its own schedule multiple times. Every delay costs money. Every cost increase triggers another round of budget negotiations. The political window for funding an ambitious lunar program is not infinite. The reasons for those delays are more revealing than the delays themselves. The Artemis program's repeated delays and what each setback reveals about how hard returning to the moon actually is. In 2017, NASA announced the Artemis program with a stated goal of returning humans to the moon by 2010-4. That date has since been moved to 22,000, then to 22,007, and current realistic assessments from inside and outside the agency suggest a crewed lunar landing is unlikely before the end of the decade. Each delay is a diagnostic. Each one points to a specific technical, financial, or organizational challenge that turned out to be harder than the schedule assumed. The Space Launch System took years longer to develop than planned and cost roughly 2 to 3 times its original budget estimate. NASA's Office of Inspector General found that the cost per launch was reaching approximately $4 billion per mission, a figure that prompted pointed questions about whether the program was financially sustainable at any meaningful flight rate. The Orion capsule, designed to carry astronauts to lunar orbit, encountered heat shield issues discovered during the Artemis 1 uncrewed test flight in 2002. When engineers examined the heat shield after re-entry, they found unexpected ablation patterns, meaning the material designed to burn away in a controlled manner during re-entry was behaving differently than models predicted. Understanding what caused that and verifying the design would be safe for a crew required additional testing and analysis, pushing the crewed mission further out. The Human Landing System, the vehicle designed to carry astronauts from lunar orbit down to the surface, was awarded to SpaceX in 2201. That decision triggered a legal challenge from Blue Origin, which delayed the program for months. Development of the lunar version of the Starship spacecraft, which SpaceX is building for this role, has itself encountered multiple schedule adjustments. Spacesuits for the lunar surface have been a problem for years. NASA's existing extravehicular suits were designed for the International Space Station environment and are not suited for lunar surface operations. Developing new lunar surface suits has faced engineering challenges, budget shortfalls, and multiple redesigns. What each of these delays shares is the same underlying reality. Returning to the moon is an engineering challenge of extraordinary scope, and the 50-year gap between Apollo and Artemis means that much of the institutional knowledge, supply chains, and specialized workforce required to do it at scale had to be rebuilt from a much lower baseline than anyone in the early Artemis planning phase fully accounted for. The Apollo program had the advantage of building everything from near scratch in a period of intense institutional focus, enormous funding, and a single overriding priority. Artemis is being built inside a complex modern aerospace ecosystem, with multiple competing priorities, a cost consciousness shaped by post-Columbia caution, and international partners whose own schedules introduce additional variables. The delays are frustrating. They are also honest signals from the engineering reality of the problem. Every schedule that slipped did so because the actual work revealed something harder than the plan assumed, and the work revealed something else, something that no government program had accounted for when the Artemis planning began. A private company had quietly changed the cost structure of getting to space entirely. Why private companies like SpaceX changed the math on moon travel, and why cost alone was never the real barrier. When SpaceX launched its first Falcon 9 rocket in 2010, the aerospace establishment treated it with a mixture of skepticism and mild amusement. Private companies had tried to build orbital rockets before, and failed. The engineering was considered too complex, the margins too thin, and the required investment too large for anyone outside a national government to sustain. SpaceX proved that wrong systematically and publicly. The Falcon 9 achieved something no government program had managed at scale: rocket reusability. By landing the first stage booster after launch and flying it again, SpaceX reduced the per-launch cost of getting cargo to orbit by a factor that shook the entire industry. A Falcon 9 launch costs roughly $60 to $70 million. A space launch system launch costs roughly $4 billion. Both can put astronauts in space, though the payloads and destinations differ significantly. The cost difference changed the conversation about the moon. Suddenly, a return mission did not require the political urgency of a space race to justify the budget. Commercial operators could theoretically fund lunar missions, at least robotic ones, at a price point that made business cases imaginable. NASA embraced this shift through its Commercial Lunar Payload Services program, contracting private companies to deliver scientific instruments and technology demonstrations to the lunar surface ahead of crewed missions. Intuitive Machines landed a small spacecraft near the lunar South Pole in February of 2024, the first American soft landing on the moon in over 50 years. A private company did it. But here is where the story gets complicated. Cost was always a symptom, never the disease. The reason humanity had not returned to the moon was not primarily that tickets were too expensive. It was that the moon is genuinely physically dangerous to humans in ways that lower launch costs do not fix. A reusable rocket gets you there more cheaply. It does not solve the radiation crossing the Van Allen belts delivers. It does not fix the regolith that degrades suits and threatens lungs. It does not eliminate the solar storm that could irradiate a surface crew in hours. It does not solve the psychological isolation, the thermal extremes, the seismic activity, or the medical unknowns of extended low-gravity exposure. The private sector has introduced real and important efficiency into the equation. SpaceX's Starship, if it achieves its design goals, will be capable of delivering enormous payloads to the lunar surface at a fraction of historical costs. That matters enormously for the logistics of building a base, but building the base itself, keeping humans alive inside it for months, and understanding what the moon does to human bodies over extended stays, those problems are scientific and medical. They require time, testing, and data that no amount of engineering ingenuity replaces. The private sector sharpened the pencil. The hard questions are still unanswered, and one discovery, made by a NASA instrument aboard an Indian spacecraft in 2024, just made those questions both more urgent and more complicated than anyone expected. The moon's south pole and the confirmed water ice hiding in permanently shadowed craters. Why this discovery made the moon worth fighting over again. There are places on the moon where sunlight has never reached. Craters near the poles sit at angles so steep, and the moon's axial tilt is so slight that their floors have been in total darkness for billions of years. No photon from any star has touched the ground at the bottom of some of these craters in longer than the dinosaurs have existed. Scientists suspected for decades that these permanently shadowed regions might hold water ice, preserved by the extreme cold in the absence of any heating source. Confirmation came incrementally. In 2009, NASA deliberately crashed a spent rocket stage into one of these craters, called Cabeus, near the South Pole. The impact threw debris upward into sunlight, where orbiting instruments could analyze it. Water molecules were confirmed in the plume. The confirmation hardened over subsequent years. India's Chandrayaan mission and data from multiple orbital instruments mapped the distribution of water ice across the lunar South Pole region more precisely. Scientists now estimate that hundreds of millions of tons of water ice may exist in the permanently shadowed craters near both poles, with the South Pole containing the largest confirmed concentrations. This changes everything about the strategic logic of the moon. Water is mass. Launching mass from Earth is expensive. Every kilogram of water carried to the lunar surface on a rocket costs thousands of dollars and burns enormous quantities of propellant to get there. A self-sustaining lunar base requires enormous amounts of water for drinking, for hygiene, for growing food, and critically, for producing propellant. Water molecules can be split into hydrogen and oxygen using electricity. Hydrogen and oxygen are rocket propellant. A lunar base that can access and process local water ice can theoretically refuel spacecraft on the surface, turning the moon into a refueling depot for missions going deeper into the solar system. The cost and feasibility of missions to Mars changes dramatically if spacecraft do not have to carry all their propellant from Earth. This is the resource that transforms the moon from a scientific destination into infrastructure. the South Pole is now the most strategically valuable piece of real estate in the solar system, beyond Earth itself. Every major spacefaring nation and several private companies understand this. NASA's Artemis program targets the South Pole. China's robotic Chang'e missions have been progressively mapping and approaching the same region. India landed near the South Pole in 2003, with Chandrayaan-3 becoming only the fourth country to land on the Moon and the first to reach the South Polar region. The competition for that ice is real, and it is accelerating. And China's missions near the pole have already returned data that contains something NASA has not yet directly confirmed with human eyes. Something on the far side of the Moon that raises questions about the lunar surface and its past that the scientific community is only beginning to work through. China's lunar ambitions and what their Chang'e missions found on the far side that NASA has not yet reached. No spacecraft from the United States has ever landed on the far side of the Moon. The far side, the hemisphere permanently facing away from Earth due to the Moon's locked rotation, remained entirely unvisited by any lander until January of 2019, when China's Chang'e 4 spacecraft touched down in a crater called von Karman inside the South Pole Aitken Basin. The South Pole Aitken Basin is the largest confirmed impact crater in the solar system. It stretches roughly 1,600 miles across and descends about 5 miles below the surrounding terrain. The impact that formed it was powerful enough to have punched through the Moon's crust entirely, potentially exposing material from the deep interior that has not been accessible at any near-side landing site. Chang'e 4's rover, named Yutu-2, began examining the composition of the surface in this basin and found something that did not match the expected models. The mantle material thought to have been exposed by the ancient impact showed a mineral composition that differed from what lunar scientists had predicted based on orbital observations and near-side sample analysis. Specifically, scientists found evidence of olivine and pyroxene in proportions suggesting the impact had indeed brought deep lunar interior material to the surface. But the exact mixture challenged existing models of how the Moon's interior layers are structured. The finding is confirmed, peer-reviewed, and published. The interpretation of what it means for lunar formation models is still being worked through. Scientists debating competing hypotheses about how the Moon's mantle is layered and what the original impact that formed the basin excavated are actively referencing the Chang'e 4 data. In 2010, Chang'e 5 landed on the near side and returned samples to Earth, making China only the third nation in history to bring lunar material home, after the United States and the Soviet Union. The samples came from a volcanic region and were confirmed to be approximately 1 billion years younger than any Apollo samples, demonstrating that volcanic activity on the Moon continued far later than previous models predicted. That result reshapes the timeline of the Moon's geological history. The Moon was considered largely dead for much of its recent geological history. The Chang'e 5 samples suggest geological activity persisted closer to the present than scientists thought, which raises questions about heat sources, interior dynamics, and potentially even the timeline of any past magnetic field activity. China's program is systematic, well-funded, and escalating. Chang'e 6 landed in the South Pole Aitken Basin on the far side in 2024 and returned samples from that region for the first time in history. Analysis is ongoing. The scientific returns from China's missions are real and are being incorporated into planetary science worldwide. The geopolitical dimension is equally real. China has announced plans to establish a permanent lunar research station at the South Pole by the early 2030s. Two programs, one American-led and one Chinese-led, are heading for the same destination, and the legal framework governing who can do what when they get there was written before either program existed. The disputed Outer Space Treaty of 1967 and who actually owns the Moon's resources. A legal fight heating up right now. The Outer Space Treaty was signed in 1967 by the United States, the Soviet Union, and the United Kingdom, and has since been ratified by over 100 countries. It established the foundational legal framework for all human activity beyond Earth. Its core principle is clear. No nation can claim sovereignty over the Moon, Mars, or any other celestial body. Space is the province of all mankind. The treaty was written during the Cold War by nations whose primary concern was preventing the weaponization of space and stopping either superpower from claiming the moon the way colonial powers had claimed continents. It accomplished that goal. No country has planted a flag and declared sovereign territory on the moon. But the treaty was written before water ice was confirmed at the poles, before anyone seriously contemplated mining lunar regolith for helium-3. Before private companies began landing spacecraft on the surface, the legal framework governing a 12-person scientific expedition looks very different when applied to a commercial mining operation. The central ambiguity is whether extracting resources from the moon counts as claiming territory. The treaty bans territorial claims. It says nothing explicit about resource extraction. In 2015, the United States passed the Commercial Space Launch Competitiveness Act, which explicitly granted American citizens and companies the right to own resources they extract from celestial bodies. American law says you can mine the moon and own what you take. The Outer Space Treaty says no nation can claim the moon. The legal relationship between those two statements has never been tested in any international court. The Artemis Accords, introduced by NASA in 2200 and signed by a growing group of countries, attempt to establish a practical framework for responsible lunar operations. They include provisions for safety zones around operational landing sites, transparency about activities, and heritage preservation for historic sites like the Apollo landing locations. They do not resolve the ownership question definitively. China and Russia have declined to sign the accords. The result is a legal environment where the most strategically valuable locations on the moon, the permanently shadowed craters containing water ice near the South Pole, are simultaneously unclaimed under international law, targeted by multiple national programs, and theoretically available for commercial extraction under American domestic law. A race to be first to establish operational infrastructure in those crater regions would create facts on the ground before any legal framework catches up. The nation or entity operating a processing facility that converts crater ice into propellant first would have an enormous functional advantage, regardless of what any treaty says about territorial sovereignty. Legal scholars, space policy experts, and government bodies are actively debating how to address this before the hardware arrives. The window to establish agreed rules before the race reaches its destination is narrowing with every launch. And the radiation those crews will face once they arrive at that destination has taken on an urgency that the treaty debates do not capture. How cosmic radiation on the moon's surface, with no atmosphere to protect against it, would deliver a dangerous dose to any astronaut staying longer than a few days. Stand outside on a clear day on Earth, and cosmic radiation is hitting you constantly. High-energy particles originating from distant supernovae, from the center of the galaxy, from our own star, rain down on the planet continuously. You do not feel them. You are protected by two shields simultaneously. Earth's magnetic field deflects a significant portion of the incoming charged particles. Earth's atmosphere, roughly equivalent in shielding mass to 10 feet of water above your head, absorbs most of the rest. Step onto the lunar surface, and both shields disappear simultaneously. The moon has no global magnetic field to deflect incoming particles. It has no meaningful atmosphere. A layer of gas so thin, it is technically classified as an exosphere, barely a wisp of molecules. There is no shielding from above whatsoever. The radiation environment on the moon's surface has been directly measured. NASA's Lunar Reconnaissance Orbiter carried instruments specifically to characterize it, and astronauts on the International Space Station wear dosimeters that provide comparison data. The confirmed result is that a person on the lunar surface receives radiation at roughly 200 times the rate of a person on Earth's surface. 200 times. An astronaut spending 6 months on the lunar surface would accumulate a radiation dose exceeding the career limits currently set by NASA for International Space Station astronauts. A 1-year stay would deliver a dose that pushes well into territory where cancer risk becomes a serious and compounding concern. The radiation comes from two main sources: galactic cosmic rays, which are high-energy particles originating outside our solar system, stream through the moon continuously from all directions. They are exceptionally difficult to shield against because the most energetic ones pass through almost any material. Solar energetic particle events, sudden intense bursts of radiation from our star during solar activity. deliver large doses in hours to days. Unlike galactic cosmic rays, solar particle events can be partially shielded against with sufficient material, but the mass required for effective shielding is enormous by spaceflight standards. The astronauts on Apollo received their surface doses in days. Radiation scientists analyzing those doses estimate they were within acceptable ranges precisely because the stays were so short. A lunar base with rotating crews staying for weeks or months fundamentally changes the equation. Current shielding proposals include burying habitats under several feet of lunar regolith, which provides meaningful attenuation of galactic cosmic rays and substantially reduces solar particle event exposure. Regolith is abundant and free. Constructing a buried habitat, however, requires excavation equipment, structural engineering solutions, and a construction process that has never been demonstrated at scale in that environment. There is also a compounding factor that makes this worse: extended time in the reduced gravity of the lunar surface, about 1/6 of Earth's gravity, produces biological changes that may increase radiation sensitivity. Bone density drops, immune function changes. Research on International Space Station astronauts has documented these shifts clearly. Whether reduced lunar gravity creates the same severity of biological change as microgravity is not yet established, because no human has spent extended time on the lunar surface. The interaction between radiation exposure, biological changes from low gravity, and the psychological stress of isolation is a combination that has never been studied in a real mission environment. What simulation studies have found about the mind under those conditions is more disturbing than the physical data. The psychological isolation of a lunar base, what simulation studies found about human minds cut off from Earth with a 3-second communication delay. 3 seconds does not sound like much. A pause in a phone call, a moment of lag on a video stream. But on the Moon, that 3-second one-way communication delay, caused simply by the distance light has to travel between the two worlds, transforms every conversation with Earth into something fundamentally different from normal human contact. Ask a question, wait 6 seconds minimum for a response. Have a crisis, wait 6 seconds before anyone on Earth even hears about it. Call home to speak to your family. Every sentence lands 6 seconds late. Every emotional exchange is chopped into fragments by a gap that no technology can eliminate, because it is not a bandwidth problem. It is physics. Researchers studying long-duration space missions have identified communication delay as one of the most psychologically corrosive elements of isolation, more damaging over time than many crews anticipate during training. NASA and other agencies have run isolation simulations to study this directly. The Hawaii Space Exploration Analog and Simulation placed crews of 6 in a dome on a remote Hawaiian volcano for periods of up to 1 year, simulating Mars distance communication delays. The results documented a consistent pattern. Early in the mission, crews managed the delay well. As months accumulated, the delay began to erode the sense of connection to Earth. Relationships with people outside the dome felt increasingly abstract. Crew members described feeling that Earth was becoming emotionally distant in a way that exceeded the physical distance. On the Moon, the delay is shorter than Mars, but the physical distance is still psychologically enormous. You can see Earth from the lunar surface with your own eyes. That visibility creates a specific kind of psychological tension that researchers call the fishbowl effect in reverse. You are close enough to see home, but completely unable to reach it in any human timescale of urgency. The Russian-led Mars 500 simulation confined 6 volunteers inside a mock spacecraft in Moscow for 520 days in 2010 and 2011, simulating a Mars round trip. Researchers found measurable declines in activity levels, sleep quality, and psychological engagement across the crew as the simulation progressed. 2 of the 6 participants showed signs of significant sedentary depression in the final months. One spent large portions of his final weeks sleeping. These were highly selected, highly trained, highly motivated volunteers in a facility in Moscow where they knew Earth was just outside the door. A lunar crew would have no such psychological safety net. The commitment is total, and unlike the International Space Station, where a Soyuz or Crew Dragon capsule can return a crew member to Earth in a matter of hours in a genuine emergency, a lunar surface crew facing a medical or psychological crisis requires a rescue mission that takes days to plan and execute, even under the most optimistic scenarios. The crew dynamics that form in that environment are also poorly understood at lunar timescales. Research on Antarctic winter over cruise, the closest Earth analog to lunar isolation, consistently finds that interpersonal conflict peaks in the middle third of a long mission, and that small irritations compound into serious functional problems when people cannot escape one another. A crew of 4 or 6 living in a buried habitat the size of a small apartment for 6 months, on a world that kills instantly outside the airlock, under radiation they cannot see, with a 6-second conversation delay separating them from everyone they love, represents a psychological environment with no historical precedent. What the moon does to the ground beneath a habitat adds yet another layer of threat that most people never consider. The seismic surprise. The moon shakes. Apollo left seismometers behind that recorded moonquakes for years, some lasting over an hour. Apollo 11 landed on the moon in July of 1969. Before the crew left, they deployed a seismometer on the surface. The instrument stayed behind and kept transmitting data back to Earth for years after the astronauts came home. Apollo 12, 14, 15, and 16 each added another seismometer, creating a network of 4 stations spread across the near side. What they recorded surprised everyone. The moon shakes, regularly, measurably, across multiple categories of seismic activity that researchers spent years classifying and still do not fully understand. The first category is shallow moonquakes. These occur within the top few dozen miles of the lunar crust and can reach a magnitude of 5.5 on the same scale used for earthquakes. A magnitude 5.5 earthquake on Earth is a serious event. It knocks objects off shelves, cracks plaster, breaks windows. On the moon, these shallow quakes have an additional property that makes them more alarming for any structure sitting on the surface. They last far longer than comparable earthquakes. An earthquake of similar magnitude typically shakes for about 30 seconds to a couple of minutes, and then fades. The Apollo seismometers recorded shallow moonquakes that continued for 10 minutes. Some lasted over an hour. The moon rang like a bell, oscillating long after the initial event, because the lunar crust is dry, cold, and rigid in a way that allows seismic energy to propagate without the water-saturated rock layers that dampen tremors on Earth. The second category is deep moonquakes, originating roughly 700 miles below the surface, likely caused by tidal forces, as the moon is stretched and compressed by Earth's gravity in its slightly elliptical orbit. These are smaller in magnitude but remarkably regular, clustering in specific locations at predictable points in the lunar orbital cycle. The third category, thermal moonquakes, occurs at the lunar dawn when the surface heats rapidly after 2 weeks of cold darkness. The sudden thermal expansion of surface rock generates cracking and shaking. These are smaller and more localized, but add to the cumulative seismic environment that any surface structure must withstand. For a buried lunar habitat, these seismic realities are a structural engineering constraint of the first order. A habitat must be designed to survive repeated shaking events that last far longer than any earthquake a terrestrial building code accounts for. The regolith that would cover the habitat for radiation protection adds mass that interacts with seismic waves in ways that require careful engineering to prevent structural failure. The Apollo seismometer network operated until 1977, when NASA shut it down for budget reasons, cutting off a scientific monitoring program that was still generating new data. The seismic behavior of regions near the lunar South Pole, the target of future crewed missions, has never been directly instrumented. Scientists extrapolate from the 4-station near-side network and from orbital measurements, but the South Polar seismic environment is not yet characterized in the detail required to certify a habitat design. A NASA-funded analysis of the Apollo seismic data, published in 2203, found evidence of ongoing fault activity in the South Polar region. Scarps, cliffs formed by thrust faults, appear geologically young, meaning they may still be active. The moon is shrinking slightly as its interior cools, and that contraction is producing fresh surface fractures. A world that shakes for an hour at a time, with faults that may still be moving, underneath a habitat buried in regolith. And the moon itself is moving away from us while all of this happens. why the moon is slowly drifting away from Earth at about 1.5 inches per year, and what that means for the planet's long-term future. Every year, the moon moves approximately 1.5 inches farther from Earth. The measurement is confirmed with extraordinary precision using laser ranging experiments that bounce laser pulses off retroreflectors left on the lunar surface by Apollo astronauts. Scientists have tracked this drift continuously since 1969. 1.5 inches per year sounds trivial. Over a human lifetime, the moon moves about the length of a typical adult's body away from Earth. Nobody notices. Tides do not suddenly change. The night sky looks identical to the one your great-grandparents saw. But stretch that rate across deep time, and the implications become profound. The moon's recession is driven by tidal interaction. The gravitational pull of the moon creates tidal bulges in Earth's oceans. Earth rotates faster than the moon orbits, which means the tidal bulge is always slightly ahead of the moon in its orbit. That offset bulge pulls the moon forward, gradually transferring rotational energy from Earth to the moon's orbit. As the moon gains orbital energy, it drifts outward. As Earth loses rotational energy, its rotation slowly decelerates. Days on Earth are getting very slightly longer over geological time. The process is minuscule on human timescales. But 4.5 billion years ago, when the moon formed, it was dramatically closer. Early Earth experienced tides dozens of times more powerful than those today. Days lasted only a few hours. Running the clock forward, in roughly 600 million years, the moon will have drifted far enough that total solar eclipses will no longer occur. The moon will appear too small in the sky to completely cover the star at our solar system's center. That window of perfect alignment, the coincidence that places us in the only era when the moon and that star appear precisely the same size from Earth's surface, is temporary. We happen to exist in it. On longer timescales still, billions of years from now, the interaction between Earth and the moon will eventually reach a stable endpoint if both objects survive. The moon's drift will slow and stop when Earth's rotation slows enough to match the moon's orbital period, locking both bodies into a mutually tidally locked state. At that point, the moon would hover permanently over one side of Earth, invisible from the other hemisphere. For any human civilization on the moon at that far future moment, the geometry of home changes entirely. Earth does not rise or set, it hangs fixed in the same position in the sky forever. That is billions of years away. The immediate relevance of the moon's drift to a return mission is indirect, but real. Tidal forces are the engine of deep moonquakes. The same gravitational relationship that slowly pushes the moon outward is simultaneously compressing and stretching its interior on every orbit, generating the seismic activity the Apollo network recorded. The astronauts who flew to this slowly retreating, internally shaking, radiation-bathed world came home as changed people. The physical transformation was documented medically. The psychological transformation was quieter, and in some cases, far more lasting. The Apollo astronauts who came home changed, not just famous, but fractured, the psychological aftermath that NASA quietly documented. Buzz Aldrin was the second human being to walk on the moon. He returned to Earth, a global hero, received parades, met presidents, and then fell into a depression that he described as the most difficult experience of his life. He struggled with alcohol. His marriage broke down. For years, he could not articulate what was wrong. He eventually concluded that the problem was the absence of a next mountain. Every goal, every achievement he could imagine, sat so far below what he had already done that motivation itself stopped making sense. He wrote about it. He spoke about it publicly, with unusual honesty for a person of his generation and background. His story opened a door that allowed other astronauts to acknowledge what they had experienced. Edgar Mitchell had a spontaneous mystical experience on the return journey from the moon. Looking out the window at the starfield, he felt an overwhelming and sudden certainty that everything in the universe was connected and conscious. He described the experience as arriving without warning, uninvited, and impossible to dismiss. He spent the remaining decades of his life studying consciousness science and never returned to the aerospace career he had built before Apollo. James Irwin, Apollo 15, became a deeply religious figure after returning from the moon. He left NASA, founded a Christian ministry and organized multiple expeditions to Mount Ararat in Turkey to search for Noah's Ark. He died in 1991, describing his time on the lunar surface as the moment he felt the presence of God most clearly. These are not obscure figures having private experiences. These are men selected through the most psychologically rigorous screening process in human history, trained for years to perform under pressure, without emotional disruption, and still profoundly altered by what they saw and felt. NASA documented these outcomes quietly. The agency conducted psychological follow-up with returning astronauts, but did not publicize the results in any systematic way during the Apollo era. The institutional priority was projecting confidence and capability, acknowledging that moon missions were psychologically destabilizing to some of the most mentally resilient people ever selected for any job, did not serve that message. Researchers who have studied the Apollo astronaut cohort in later decades have noted a pattern. Those who walked on the surface showed measurably different long-term psychological profiles from those who flew to the moon but remained in lunar orbit during surface operations. The surface walkers experienced more profound identity changes, more spiritual or philosophical shifts, and a higher rate of what researchers describe as post-mission meaning-seeking behavior. Michael Collins, who orbited the moon alone in the command module while Armstrong and Aldrin walked below, was notably different. He described the experience as peaceful, almost meditative. He went on to a successful career, wrote clearly and without apparent turmoil about his experience, and seemed, by most accounts, the least psychologically disrupted of the Apollo 11 crew. The surface did something to the people who stood on it. The overview effect, compounded by physical presence on another world, created psychological shifts that training had not anticipated, and that debriefings did not fully capture. What none of them could explain rationally, and what instruments have logged but not explained, are the strange lights and sounds the moon has produced for observers across centuries. The mystery of the transient lunar phenomena, unexplained flashes and glows, seen on the moon's surface for centuries, still without a definitive explanation. For centuries, astronomers watching the moon through telescopes reported something that should not have been there. Brief, localized brightenings, colored glows, flashes, shadow-like obscurations that appeared and vanished within minutes in specific regions of the lunar surface. The reports came from credible observers using serious instruments, spanning hundreds of years in multiple countries. Astronomers catalogued these events under the term transient lunar phenomena. NASA commissioned a formal study of the historical reports in 1968, a year before Apollo 11 landed. The report catalogued over 500 individual observations, stretching back to the 9th century, documented by observers including respected professional astronomers. The phenomena were real in the sense that multiple independent witnesses reported similar events at similar locations on multiple occasions. The question of what caused them has never been definitively settled. Several explanations have been proposed, each supported by some evidence and contested by others. The leading scientific hypothesis involves outgassing. The moon is geologically not entirely dead. Small quantities of gas, including radon and helium, continue seeping from the interior through faults and porous surface regions. When these gases escape, they can disturb the surface dust electrostatically, producing brief brightenings as the charged dust scatters sunlight differently. This mechanism is confirmed to occur at some level. Whether it accounts for all reported transient phenomena is debated. Impact events offer another explanation. The moon is continuously struck by micrometeorites, and occasionally by larger objects. A fresh impact generates a flash of light and a dust cloud that could produce a temporary brightening visible from Earth. Lunar Reconnaissance Orbiter imagery has confirmed that new craters appear on the moon every year, demonstrating that impacts continue at a measurable rate. The most active site for reported transient phenomena is the crater Aristarchus, on the near side's northwestern quadrant. It is one of the brightest features on the lunar surface, sits in a region of known geologic interest, and has been the location of more logged transient events than anywhere else on the moon. Apollo crews were instructed to observe it during their missions. Buzz Aldrin reported seeing a brightening in that region from lunar orbit. The report is in the mission record. Some observations remain genuinely unexplained within any proposed framework. A 1963 event reported simultaneously by multiple observers at different observatories showed a reddish glow in the Aristarchus region lasting over an hour. The event coincided with a period of elevated solar activity, which some researchers connect to outgassing triggered by solar-wind interaction with the surface. Modern amateur and professional astronomers continue logging transient events using coordinated observation networks. The events continue to occur. Explanations continue to multiply without converging. The moon keeps producing observations that resist complete understanding. And building a permanent human presence on a world this poorly understood demands a scale of engineering ambition that reframes every other challenge discussed so far. How a moon base would need to be buried underground to protect inhabitants, and the engineering scale that makes it comparable to building a city from scratch. A surface habitat on the moon is not survivable for extended human occupation. The radiation alone makes it untenable. Add the thermal extremes, the micrometeorite bombardment, the seismic risk, and the regolith contamination threat, and a structure sitting exposed on the lunar surface becomes an engineering proposition that no serious lunar architect supports for long-duration missions. The solution that emerges from every serious design study is burial. Cover the habitat in several feet of regolith to provide radiation shielding, thermal insulation, and protection from micrometeorite impacts. Build down rather than up. Create a base that from the outside looks less like a human facility and more like a series of low mounds, its actual complexity hidden beneath the surface. That solution introduces a new set of engineering challenges on a scale that has no direct precedent in any human construction project. To bury a habitat under several feet of regolith requires moving enormous quantities of that material. You need excavation equipment capable of operating in vacuum, in extreme temperatures, powered by a lunar energy source, controlled either autonomously or by an operator who may be several seconds delayed in communication with Earth. Every machine that does this work must be launched from Earth or assembled on the surface, and every component must survive the transit and deployment process. The habitat structure itself must be engineered to bear the load of covering material while withstanding the seismic environment documented by the Apollo network. Standard terrestrial building materials and designs do not directly translate. Structures must be pressure vessels maintaining an internal atmosphere against the vacuum outside, while simultaneously bearing compressive load from above and thermal stress from the cycling between day and night temperatures. A team of researchers at MIT and NASA's Marshall Space Flight Center has studied the use of lunar regolith itself as a building material, sintering it into bricks using concentrated sunlight or microwave energy. Laboratory tests have produced bricks of adequate compressive strength. Whether this process can be scaled to produce enough material for a habitat structure using equipment that can realistically be transported to the lunar surface is still undemonstrated. A realistic initial lunar base, capable of supporting 4 to 6 crew members, would require a pressurized volume roughly equivalent to a modest apartment complex. Power requirements for life support, scientific equipment, communication systems, and the electric rovers needed for surface operations would demand a power plant producing several tens of kilowatts continuously through the lunar night. Solar panels cannot provide that through 2 weeks of darkness. Nuclear fission power, specifically NASA's Fission Surface Power Project, is the current leading solution. A small fission reactor capable of powering a lunar base has been designed and ground-tested in components, but has not yet been deployed in space. Water processing from crater ice, air recycling, food production, medical facilities, emergency systems, all must be present and redundant because the nearest resupply is days away under ideal circumstances. Designing the engineering is one challenge. Building it remotely, using robotic systems that must operate autonomously in an environment never fully tested at scale, before the crew arrives, is the harder one. And inside that buried base, beneath the regolith, the resource that may drive the next era of energy technology is waiting in the soil above them. The helium-3 energy source locked inside the moon's soil, a fuel for fusion reactors that does not yet exist, driving a resource race before the technology catches up. The moon's surface soil contains something that Earth has almost none of: a variant of the element helium called helium-3, deposited over billions of years by the constant stream of particles flowing from the star at the center of our solar system. On Earth, the atmosphere and magnetic field deflect this stream. The Moon, with neither protection, has absorbed it directly into the top few meters of its regolith across geological time. Helium-3 is not radioactive. It does not produce neutrons as a byproduct when used in a fusion reaction. Those two properties make it, in theory, an almost ideal fuel for a fusion reactor. Fusion using helium-3 and a hydrogen isotope called deuterium would produce protons instead of neutrons, which are easier to capture as usable energy and do not irradiate the reactor structure the way neutron-producing reactions do. The estimated energy density of helium-3 is extraordinary. Scientists calculate that roughly 25 tons of helium-3, fully consumed in a fusion reactor, could provide enough electricity to power the entire United States for approximately a year. The Moon is estimated to hold around 1 million tons of helium-3 in its surface soil. Here is the problem. No working helium-3 fusion reactor exists. Fusion power in general, the goal of sustaining a controlled fusion reaction that produces more energy than it consumes, has been pursued for decades and remains just beyond operational capability. Several fusion programs, including the International ITER project and private ventures like Commonwealth Fusion Systems, are making genuine and accelerating progress. But a reactor specifically designed to use helium-3 as fuel requires solving additional engineering challenges beyond baseline fusion. The resource race for the Moon's helium-3 is therefore a race for a fuel that serves a technology still under development. Nations and private entities are positioning to access the resource before any machine exists to use it efficiently. This is not inherently irrational. Mining and stockpiling a resource before the infrastructure to refine it is complete is standard industrial strategy. The companies extracting lithium from salt flats in South America were selling it into a battery industry that was still maturing. The parallel is not perfect, but the logic is familiar. What makes the lunar helium-3 race distinctive is the scale of the challenge involved in extraction. Helium-3 is dispersed through the regolith at concentrations of roughly 10 to 20 parts per billion. To extract 25 tons would require processing an area of lunar surface roughly the size of Washington state to a depth of several feet. The equipment required is massive, the energy needed for processing is enormous, and the entire operation must function in the lunar environment described across the preceding chapters. The economics of helium-3 mining depend entirely on the development of fusion reactors that can use it efficiently. Those reactors do not yet exist. The Moon holds the fuel, the engine is still being built. And the human body that would operate any of this equipment faces changes that no amount of engineering resolves, because gravity itself is altering the biology of any crew that stays long enough to do the work. Why returning to the Moon requires solving a medical problem nobody expected. Bone density loss so severe that astronauts landing after months in space could fracture their legs just walking. Spend 6 months aboard the International Space Station, in the microgravity of low Earth orbit, and your skeleton begins to unlearn what gravity requires of it. Without the constant mechanical stress of supporting your own weight, the body interprets bone tissue as surplus and begins reabsorbing it. Bone density drops at roughly 1 to 2% per month in key load-bearing regions, particularly the hips, spine, and lower legs. Muscle mass atrophies. The cardiovascular system restructures itself around a fluid distribution that no longer pools in the legs. Returning astronauts from long-duration space station missions land in a medical support environment designed around this reality. They are carried out of the Soyuz or Crew Dragon capsule. They sit in reclining chairs during the initial medical checks. They do not walk normally for hours to days. They receive months of structured physical rehabilitation before their bodies return to pre-mission baseline. Some astronauts never fully recover their peak bone density. The Moon's gravity is 1/6 of Earth's. It is greater than the zero gravity of the space station, which means the body would experience more loading than in orbit. Researchers expect bone loss on the lunar surface to be less severe than on the International Space Station, but still significant. The exact rate is unknown because no human has spent months in lunar gravity, and Earth-based simulations of 1/6 gravity cannot be sustained for the durations needed to generate reliable longitudinal data. Here is the medical danger that engineers almost never discuss in press releases. A crew spending 6 months on the lunar surface will have experienced partial gravity throughout. When they return to Earth and land, they re-enter full gravity with a body that has partially adapted away from it. The load-bearing capacity of their bones and muscles will be reduced. The risk of fracture during that transition period is real, documented in returning space station crews, and expected to be present in any lunar surface crew. Exercise countermeasures on the International Space Station, 2 hours of structured resistance and cardiovascular exercise daily, have reduced but not eliminated bone and muscle loss in long-duration crews. A lunar base must include equipment capable of providing meaningful mechanical loading to crew members throughout their stay. The mass budget required for adequate exercise equipment competes with every other system on the Habitat Manifest. Beyond bone loss, the vision changes that have emerged as one of the most concerning long-duration spaceflight findings add another layer of medical uncertainty. A condition called spaceflight-associated neuroocular syndrome causes measurable changes to eye structure and vision in a significant fraction of International Space Station astronauts on long missions. The mechanism involves fluid shifts in microgravity affecting pressure inside the skull. Whether 1/6 lunar gravity produces the same effect at the same rate is confirmed to be a concern but is not yet characterized in real mission data. A future lunar crew may return to Earth with reduced bone density, altered vision, and cardiovascular systems that need weeks to readjust to full gravity. Designing the return and recovery protocols for that crew is a medical and logistics challenge that currently rests on incomplete data. The missions closest to testing what extended lunar stays do to human physiology are the ones Apollo came closest to achieving and then abandoned. What those missions had planned and how close they came to disaster reveals how narrowly the program thread its way through catastrophe every single time it flew. The backup plans NASA never used, the secret abort procedures and survival scenarios engineered for Apollo that reveal how close to catastrophe every mission actually flew. Every Apollo mission carried, alongside its public mission profile, a complete architecture of failure scenarios. Engineers at NASA and its contractors had modeled, planned for, and in some cases built hardware around the possibility that things would go wrong. The public saw the triumphs. The backup plans reveal how thin the margin was. Apollo 13 is the known case. An oxygen tank in the service module ruptured on the way to the moon in April of 1970. Crippling the spacecraft's power and life support systems. The crew used the lunar module as a lifeboat, looping around the moon and returning to Earth using a trajectory that required extraordinary improvisation in thermal management, power conservation, and navigation calculation. They survived. The mission was called a successful failure. What receives far less attention are the abort modes built into every single mission that Apollo 13 simply happened to require for real. During the powered descent to the lunar surface, astronauts had a precise window of decision points called abort gates. At each gate, if a critical system failed, a different abort mode would execute. An abort early in descent would fire the ascent engine while still high, returning the crew to orbit. An abort later in descent, after the landing legs had deployed, required firing the ascent engine from close to the surface. An abort after landing, if the ascent engine failed to ignite for any reason, had no survivable outcome. NASA engineers acknowledged this in internal documents. If the ascent engine failed on the surface, the crew died. There was no rescue capability, no second chance. The ascent engine carried no redundant ignition system in the traditional sense. It used hypergolic propellants, chemicals that ignite on contact with each other, removing the need for a spark. But the valve system controlling the propellant flow had to work, every time, on a world with no backup. Engineers were so aware of this single point of failure that the astronauts themselves were briefed on manual workarounds, including using a felt-tip pen to jam the circuit breaker that controlled the ignition circuit on Apollo 14, after mission controllers discovered the original breaker had a fault that could have prevented engine ignition. Buzz Aldrin pressed a pen into a damaged circuit breaker. If that had not worked, the mission ended permanently on the surface. Apollo 17 carried a crumpled fender on the lunar rover, damaged accidentally during suit-up. Without the fender, the rover sprayed abrasive regolith over the crew and equipment during driving, threatening to overheat the astronauts and damage suit seals. Mission controllers devised a repair using maps, clamps, and duct tape, improvised on Earth and relayed to the surface. The repair worked. Each mission flew within a structure of contingencies that mostly held. The ones that failed partially, like Apollo 13, revealed the depth of the engineering safety net built beneath the program. The ones where the safety net might have failed entirely, like Apollo 14's ignition circuit, revealed how close improvisation and luck stood to the mission's survival. A return to the moon inherits this same fundamental truth. Environments that will kill in seconds require engineering margins that account for every conceivable failure. And the history of Apollo demonstrates that the unconceivable failures are the ones that actually arrive. What the unconceivable holds in the permanently shadowed craters waiting at the South Pole may be the most scientifically extraordinary finding of all. What the moon's permanently shadowed craters might contain beyond water, ancient organic molecules preserved in the coldest natural places in the entire solar system. The permanently shadowed craters near the lunar poles are cold in a way that requires a different relationship with the word. Temperatures in the deepest sections reach around -400 degrees Fahrenheit. To provide context, the surface of the planet Neptune, the outermost planet in our solar system, averages around -350 degrees. Some of the coldest lunar crater floors are colder than a planet 4.5 billion miles from the center of our solar system. At those temperatures, chemistry essentially stops. Molecules do not react. They do not break down. They do not change. They persist in whatever state they arrived in, potentially for billions of years. Scientists analyzing the full inventory of confirmed and suspected materials in the permanently shadowed regions have found evidence suggesting the presence of more than just water ice. Spectral analysis from orbiting instruments has detected signals consistent with additional volatile compounds, carbon dioxide, ammonia, methane, and tantalizing hints of more complex organic compounds. Organic molecules are carbon-based compounds, the molecular building blocks associated with biological chemistry. Their presence on the moon does not imply life. The moon shows no evidence of biology. But organic molecules arrive on planetary bodies via comets and asteroids, the same delivery mechanisms that some scientists believe seeded early Earth with the chemical precursors that eventually led to life. The permanently shadowed craters on the moon may contain an essentially undisturbed record of what comets and asteroids have been delivering to the inner solar system across billions of years. A chemical archive of the early solar system, frozen and preserved with extraordinary fidelity in the coldest places accessible to human missions. The scientific value of samples from these regions, analyzed in the context of what is known about Earth's early chemistry and the origin of life question, is difficult to overstate. Astrobiologists and planetary scientists describe the permanently shadowed regions as among the highest priority targets in solar system science, specifically because of what the cold may have preserved. Accessing them is an enormous challenge. These craters never receive sunlight. Solar panels produce no power inside them. Rovers must carry their own power source or receive it via relay from crater rims. Temperatures that preserve the science also threaten the electronics required to collect it. Many standard electronic components fail at the temperatures found in the deepest shadowed regions. NASA's Volatiles Investigating Polar Exploration Rover project, a small robotic rover called Viper, was designed to drive into shadowed regions near the South Pole, map the ice distribution, and sample subsurface material. The mission was cancelled in July of 2024 due to budget constraints after the rover had been largely built, a decision that drew significant criticism from the planetary science community. The science is there. The resources may be there. The legal framework for who gets to access it is contested. The geopolitical competition to reach it first is accelerating, and the next decade will determine whether any of this proceeds as international collaboration or as a new version of a territorial competition humanity has already played out badly on Earth. The geopolitical flashpoint, why the moon's south pole has become the center of a new space race that mirrors Cold War tensions more than cooperation. Two flags are heading for the same crater. The United States, through the Artemis program, has targeted the lunar south polar region for its first crewed landing since Apollo 17. China, through its robotic program and its announced International Lunar Research Station project, has targeted the same region for its robotic precursor missions and its planned crewed presence by the early 2030s. Russia has formally partnered with China on that station, rather than signing the Artemis Accords. The convergence on a single small geographic area of the Moon is driven entirely by the water ice, confirmed in the permanently shadowed craters. Every operational and scientific argument for a sustainable lunar presence leads to the same place. That place is the South Pole. And the South Pole is not large enough for both programs to operate without awareness of and potential interference with each other. NASA Administrator Bill Nelson stated publicly in 2203 that the United States is in a race with China for the Moon's resources, and that he takes that competition seriously. The statement was notable for its directness. American officials do not typically frame scientific exploration programs in explicitly competitive geopolitical terms. The fact that Nelson did reflects how clearly the strategic dimension of the South Polar region is understood inside the agency. The Artemis Accords, which attempt to establish norms for lunar operations, have been signed by over 40 countries as of early 2205. The signatories are predominantly allied with or friendly toward the United States. China, Russia, and several other major spacefaring nations are absent from the list. The result is two emerging camps in cislunar space, broadly mirroring existing geopolitical alignments on Earth. The accords include provisions for safety zones, areas around an active operation where other parties agree not to interfere. The legal basis for enforcing these zones against a non-signatory nation has never been tested. The mechanism for resolving a dispute where two programs want to operate in the same crater is not established. No international treaty currently prevents a nation from landing a spacecraft adjacent to another nation's facility and conducting operations that functionally compromise the other party's access to resources or safety. The Outer Space Treaty prohibits interference with another nation's equipment, but defining what constitutes interference as a location where both parties have legitimate interests is a legal and diplomatic problem without precedent. The scenario that concerns analysts most directly is a race to establish the first operational water extraction facility in a high-value crater near the South Pole. The entity that reaches operational status first, whether a national program or a commercial operation operating under a national license, creates a physical presence that subsequent arrivals must navigate around. Priority of presence becomes a form of informal territorial claim, even without the formal claim the Outer Space Treaty prohibits. History on Earth offers no encouraging precedent for how competing powers navigate contested resource locations without a governing framework both recognize. The Antarctic Treaty System provides one model. The Law of the Sea provides another. Both took decades and significant political effort to establish. The timeline for establishing their lunar equivalent may already be shorter than the arrival of the hardware that will make it urgent. When that hardware does arrive, the question of survival on the surface it reaches will hinge on one threat that no political agreement addresses: how a single solar storm could irradiate an unprotected moon base in hours, and why predicting them well enough to guarantee safety is still beyond current science. On September 1st, 1959, astronomer Richard Carrington was sketching sunspots through his telescope when he witnessed a sudden, brilliant white flare erupting from the surface of the star at the center of our solar system. Within hours, telegraph systems across Europe and North America failed. Aurora lights appeared as far south as Cuba and Hawaii. Some telegraph operators reported receiving shocks from their equipment even after disconnecting the power. The magnetic disturbance lasted for days. The Carrington event, as it became known, was the most powerful solar storm in recorded human history. It struck Earth in an era before electric grids, satellites, or digital communications. Scientists analyzing the paleoclimate record from ice cores and tree rings have since identified evidence suggesting storms of similar or greater magnitude may occur on timescales of centuries. A Carrington-scale event directed at Earth today would represent a civilizational disruption. Satellites would fail. Power grids across wide regions could experience damage requiring years to repair. The economic losses would be measured in trillions of dollars. On the Moon, a similar event would be immediately and personally lethal to any unprotected crew. The most energetic solar particle events can deliver a lethal radiation dose to an unshielded human in hours. The Moon has no atmosphere and no global magnetic field to intercept any of it. A crew performing a surface excursion in spacesuits when a major solar particle event arrives faces a situation with a narrow window for response. Get underground, behind sufficient shielding mass, as fast as possible. The engineering response to this threat is a storm shelter, a dedicated, heavily shielded volume within the habitat, essentially a small room surrounded by additional layers of water, polyethylene, or regolith, where the crew retreats during a solar event. This is confirmed in all serious lunar-based design proposals. The critical variable is warning time. NASA operates a space weather prediction program that monitors solar activity and issues alerts when major events are detected. For events originating from active regions on the side of the star facing Earth, warning times of 15 minutes to a few hours are achievable. That is adequate for a crew inside the habitat to move to a storm shelter. The dangerous scenarios involve events originating from active regions the monitoring systems cannot see, on the far side of the star relative to Earth, or storms that escalate faster than predictive models anticipate. Solar physics research has advanced significantly in recent decades, and spacecraft positioned at additional viewpoints around the solar system improve coverage. But the ability to predict a major solar particle event with certainty and adequate lead time remains an open research problem. A crew conducting a surface excursion 2 miles from the habitat when a storm arrives has a very different survival scenario than a crew already inside. Surface mobility plans for lunar astronauts must account for storm risk, keeping crews within safe return distance of the habitat at all times based on current space weather status. The geology beneath that habitat and the stars above it are both potentially lethal, and every variable discussed across these chapters — radiation, regolith, seismicity, biology, psychology, thermal extremes, legal uncertainty — depends on an overarching problem that engineering alone cannot solve. The simulation problem. We have never tested a full lunar-based system end-to-end on Earth, meaning the first real mission carries unknowns that no amount of modeling fully removes. Every system proposed for a lunar base has been tested, in components, in laboratories, in analog environments on Earth that approximate one or two features of the lunar surface, while missing others. No one has ever assembled all of those systems simultaneously in a real lunar environment and run them together long enough to find every failure mode. This is the simulation gap, and it is one of the most consequential limitations facing the Artemis program and every other lunar architecture under development. Consider what a full system test would actually require. You need lunar gravity, 1/6 of Earth's, sustained for months. No Earth-based facility can provide that. Partial gravity simulations using underwater environments or aircraft flying parabolic arcs last seconds to minutes. Sustained 1/6 gravity testing for the duration of a lunar mission does not exist on Earth. You need vacuum. Long-duration vacuum testing of full habitat systems at scale is enormously expensive and operationally complex. Components are tested individually in vacuum chambers. Testing an entire integrated habitat with crew present in vacuum for months is impractical on Earth. You need real lunar regolith. The approximately 800 pounds of lunar material returned by Apollo is scientific treasure, used almost exclusively for analysis. Lunar simulants, materials engineered to approximate regolith's properties, have been developed and used for equipment testing. Every simulant fails to perfectly replicate some property of the real material. The electrostatic charging behavior, the specific mineralogy, the particle size distribution at the nanoscale level. No simulant exactly matches all of them simultaneously. You need the real radiation environment. A ground-based facility cannot replicate the full spectrum of galactic cosmic rays and solar energetic particles that a crew on the Moon would experience. Some particle accelerator facilities can approximate specific components of the radiation environment for short testing periods. None can sustain that environment for months. What engineers can do, and have done extensively, is model each system individually with high fidelity, test components and subsystems in relevant partial environments, and use analog missions in places like Antarctica, the Utah Desert, and undersea research habitats to study human performance and system integration in isolated environments. All of that work is genuinely valuable. It identifies problems early. It builds operational knowledge. It refines designs. It does not replace finding out what actually happens when the full system runs in the real environment. Apollo engineers faced the same simulation gap. The Apollo program discovered things about the lunar environment and about human performance in it that ground testing had not predicted. The regolith behavior was more aggressive than simulant testing suggested. The visor fogging during extravehicular activity was worse than expected. The communications antenna had to be repositioned mid-mission on Apollo 11 because the geometry of Earth's position in the sky relative to the landing site was slightly different from training simulations. Every mission to the moon will carry a final category of unknowns that no simulation eliminates. The question is not whether unknowns will exist. They will. The question is whether the engineering margins, the crew training, and the mission architecture are robust enough to absorb surprises without becoming fatal. The data informing those margins comes partly from what happens to bodies in partial gravity over extended time. And the honest answer is that we do not yet fully know. What happens to a human body after 6 months on the moon's surface? The confirmed physical changes that science has measured in astronauts on the International Space Station applied to lower gravity. No human has spent 6 months on the moon. The data does not exist. What science can do is take what is known from 6-month International Space Station missions, apply what is understood about the physics of 1/6 gravity, and project the expected physiological picture. The result is sobering. After 6 months on the International Space Station, the average returning astronaut has lost roughly 10% of bone density in the hip and spine. Their leg muscles have atrophied significantly, sometimes requiring assistance to stand and walk initially. Their cardiovascular system has redistributed fluid upward, reducing the blood volume in the lower body and requiring the heart to relearn how to pump against full gravity. Their immune system shows measurable dysregulation. Their sleep quality has declined. A significant fraction shows the vision changes associated with spaceflight-associated neuroocular syndrome. Recovery takes months. Some changes, particularly in bone density and vision, may not fully reverse. Long-duration astronaut Scott Kelly, who spent nearly 1 year on the station, showed genetic expression changes measured against his twin brother, demonstrating that spaceflight alters biological function at the cellular level in ways that persist after return. Apply this to a lunar mission. 1/6 gravity provides more mechanical loading than 0 gravity. The body is not in freefall. Weight-bearing exercise is possible in the natural environment, rather than requiring dedicated equipment for every loaded movement. Researchers expect the rate of bone loss and muscle atrophy to be meaningfully lower on the moon than on the station. The exact reduction factor is genuinely unknown. What is known is that 1/6 gravity does not protect fully. Bed rest studies on Earth, where participants lie flat for extended periods to simulate unloading, show bone loss even under Earth's full gravity when mechanical loading is removed from the skeleton. 1/6 gravity provides some loading, but specific bones, particularly in the spine and hip, may still experience significant adaptation over months. The fluid shift effects and vision changes may behave differently in partial gravity than in 0 gravity. Researchers predict the effects would be reduced but present. The actual data will not exist until crews spend months there and return with medical records. The crew that returns from a 6-month lunar mission will land in full gravity with bodies that have partially adapted away from it. The first hours after landing represent peak risk for musculoskeletal injury. Medical support teams at the landing site will need protocols designed around this reality, including mobility assistance, immediate orthopedic assessment, and a rehabilitation timeline that accounts for the specific combination of partial gravity adaptation, radiation exposure, and psychological decompression. No returning crew from the moon has ever been met with this medical protocol because no crew has stayed long enough to require it. The first crew that does will be writing the playbook in real time, informed by the station data, but operating beyond the edge of direct human experience. The stakes of that mission extend beyond the crew. What they experience, medically, psychologically, and scientifically, will determine whether a permanent lunar presence is a realistic future for our species, or a goal that requires a generation more of preparation. Every question asked across these 31 chapters converges on a single decade ahead, a window that scientists, engineers, and policymakers describe as genuinely decisive. The philosophical weight of going back, whether humanity returns to the moon out of curiosity, survival, or competition, determines everything about how we treat it when we get there. The 12 men who walked on the moon left behind more than boot prints and equipment. They left flags, 6 American flags, planted at 6 landing sites across the near side, symbols of a nation rather than of humanity. The choice was deliberate and contested even at the time. Some at NASA wanted a United Nations flag, or no flag at all, on the grounds that the moon belonged to no nation. Politics prevailed. Those flags are still there. Radiation and thermal cycling have likely bleached them white by now. The gesture that planted them matters more than their current condition. It tells something essential about the motivation that drove the program. Apollo went to the moon to win. That engine was powerful enough to achieve something extraordinary. It was not powerful enough to sustain a program beyond its geopolitical objective. The return to the moon is being driven simultaneously by multiple motivations, and the tension between them will shape everything about what humanity does when it arrives. Competition, scientific curiosity, resource extraction, and the long-term survival argument for becoming a multi-world species all pull in directions that align partially and conflict in others. A mission driven purely by competition, as Apollo largely was, produces the fastest results and the least durable infrastructure. Win the race, plant the flag, declare victory. The South Pole's water ice does not care about flags. Extracting it, processing it, and using it to fuel a sustained presence requires stability, investment, and time horizons that outlast political administrations. A mission driven purely by science produces extraordinary data and no incentive for the scale of infrastructure that a permanent base requires. Science funding flows toward knowledge, not toward construction projects that cost hundreds of billions of dollars. Resource extraction as a primary driver raises questions that the treaty debates of Chapter 16 only begin to address. Who benefits from lunar resources? The company that extracts them? The nation that licenses the company? All of humanity, as the Outer Space Treaty's language suggests. The economic model of lunar mining will be set by whoever gets there first and begins operations before governance catches up. The survival argument, the idea that spreading humanity across multiple worlds reduces existential risk from any single catastrophic event, is philosophically compelling and enormously distant in practical terms. A lunar base of 6 people is not a survival colony. It is a scientific outpost. Genuine redundancy of human civilization requires a self-sustaining off-world population capable of persisting without resupply from Earth, a goal that is centuries away under any realistic assessment. Edgar Mitchell, who had his mystical experience on the return from Apollo 14, spent years afterward arguing that the overview effect, the shift in perspective that comes from seeing Earth as a small, fragile object in an indifferent cosmos, was the most important thing any human had brought back from the moon. His argument was that the experience of genuinely understanding Earth's smallness and vulnerability was the most practical tool available for addressing the conflicts and environmental challenges facing the species. Whether that argument moves any budget committee is another question. Whether it should move more of them is one worth sitting with. The answer to why we go back will determine what we do when we arrive, and what we do when we arrive will echo across the rest of the century. The window of return, the Artemis timeline, the international race, and the single decade scientists say could define whether humans become a multi-world species or retreat permanently to Earth. Sometime in the late 2020s, if current trajectories hold, a small group of human beings will stand on the moon again for the first time in more than half a century. The engineering that will carry them is more capable than Apollo's. The scientific knowledge guiding them is incomparably richer. The geopolitical environment surrounding them is more complicated than anything the Apollo program faced. The decade between now and the mid-2030s represents by the assessment of multiple research communities and space policy institutions, a genuine decision point for human civilization's relationship with space. The reasoning is specific. Current launch cost reductions, driven primarily by reusable rocket development, have opened a window in which lunar infrastructure becomes economically imaginable for the first time since Apollo. That window is not permanent. The industrial momentum and political attention that sustain large space programs are cyclical. They have closed before. At the same time, the geopolitical competition between the United States-led Artemis Coalition and the China-Russia International Lunar Research Station program is generating a level of sustained political will that historically has been the only reliable driver of the investment scales lunar programs require. Competition built Apollo. Competition is currently the strongest structural force sustaining Artemis through its delays and cost overruns. Scientists studying the permanently shadowed crater regions argue that the first decade of human presence near the South Pole will determine the framework within which all subsequent lunar activity occurs. The entity that establishes operational water extraction first writes the template. The legal and operational norms established in the first years of active crewed South Polar operations will persist. The way the precedents established in early aviation governance persisted long after the technology that inspired them had transformed beyond recognition. If the Artemis program achieves a crewed landing in the late 2020s and begins building toward a sustained presence, the momentum generated could carry human activity on the Moon forward into a phase from which withdrawal becomes politically and economically difficult. Infrastructure creates its own argument for continuation. If the program slips further, if budget pressures, political transitions, or a major accident break the current momentum, the window narrows. The engineering workforce disperses again, as it did after Apollo. The supply chains retract. The institutional knowledge begins its slow erosion. Returning from that position requires rebuilding from a lower baseline, at greater cost, against a competitor that may have used the interval to establish a presence the United States would then be trying to catch. The stakes are therefore not simply about planting a flag or harvesting water ice, or finding ancient organic molecules. The stakes are about whether the organizational, technical, and political capacity to extend human presence beyond Earth reaches a self-sustaining threshold before the forces that tend to collapse large programs succeed in doing so again. Eugene Cernan climbed that ladder in December of 1972. He looked down at his boot print in the dust and became the last human being to leave a world other than Earth. He thought he was leaving temporarily. He did not know he was leaving for more than 50 years. He died in 2017 without going back. The next boot print is not guaranteed. The window is open. Whether humanity steps through it, and why, and with what intentions, are questions being answered right now in budget hearings and rocket tests, and political decisions made by people who may never see the Moon themselves. But someone will. The only question is when, and what we do when we finally get there.